Today's lesson 1 of Unit 6, and we're looking at exploring exponential models. So to start with, we're going to look at the general form of an exponential function, and that would be this equation right here. Y is equal to a times b to the power of x. So exponential growth, if it was graphed, looks like this one here. An exponential growth starts close to the x-axis and rapidly increases. Exponential growth happens when your a value is greater than 0. And when I'm talking about a value, we're looking at this equation. Your a value is greater than 0, and your b value is greater than 1. If we take a look at exponential decay rapidly decreases and then starts to level off. Exponential decay occurs if a is greater than 0, and if b is between 0 and 1. It cannot be less than 0. So knowing this about our a and b value, knowing that if b is greater than 1 and it's exponential growth, and if b is between 0 and 1, it's exponential decay, we're going to come down here and we're going to look at the general form of exponential growth or decay. So for the first one, actually before I even start, let's write the general form, which is y equals a times b to the power of x. Notice that b is the base of the exponent. All right, for number 1, we have 12 times 0.95 raised to the power of x. In this case, 12 is our a value, and 0.95 is our b value. 0.95 right here is between 0 and 1. That would tell us that this is going to be exponential decay. For number 2, we have an a value of 150. We have a b value of 1.29. In this case, b is greater than 1, and this would represent exponential growth. If we look at example 1 and 2, I'm going to highlight the base and the exponent on both of these. Now let's take a look at number 3. Number 3 is 1,000, which is your a value, times 1 minus 0.28. 1 minus 0.28 needs to be consolidated in order to get that single b value. So I'm going to rewrite this as 1,000 multiplied by 0.72 raised to the power of x. Now we have a single base with our exponent, and that base is between 0 and 1, so we will say this is decay, specifically exponential decay. And number 4, we need to do the same thing. We have our a value as 48. Our b value is 1 plus 0.12. We need to consolidate to create a single b value of 1.12 raised to the power of x. And that gives us our b value of 1.12, which is larger than 1. So this is an example of growth. This section right here is the absolute basics of exponential growth or decay. So we're going to move on to word problems, but don't forget this general form. The general form is very important. So moving into what exponential growth and decay is, you can see in this little write-up right here, it says a common application of exponential growth is compound interest. So we're going to focus on some interest functions. And when we're talking about compound interest, we're talking about things like bank accounts or investments. So things that are going to earn interest. something that you're probably familiar with or at least have heard something about at some point or other. The first formula we're going to look at is going to be the periodic compound interest formula. And the periodic compound interest formula is when you are specifically dealing with interest that is either compounded annually, semi-annually, quarterly, monthly, weekly, or daily. And for this, we fill in this equation. We have A, which is equal to the account balance. We have this set equal to the principal or the amount invested, so it's whatever you start with. I should put starting point as an extra note. The equation goes 1 plus R. R is the rate as a decimal. So for example, if you had a 2% interest rate, meaning you had a bank account that was earning 2% interest, you would need to write this in the formula as 0.02. That's the decimal. So you move the decimal place over 2 places to get the form we're looking for. All right, so the rate is going to be divided by the number of times compounding per year. And the number of times compounding per year are these values that we talked about. If it's annually, your end value is 1. Semi-annually, the end value is 2. Quarterly, end value is 4. Monthly, end value is 12. Weekly, your end value is 52. And daily, your end value is 365. Use these. Don't make up new values. Use the ones that I gave you. All right, so after we fill in 1 plus the rate over the number of times compounding, we have an exponent, which is the number of times compounding again, multiplied by the time in years. It's important to know that the time is in years. If by chance something gives you the time in months, you need to calculate that out to the decimal of a year. If we compare this equation that I just gave you to the equation on the first page, which was the general exponential form, and the general exponential form was a times b raised to the power of x. If we compare these two formulas, they are the same. Your b value is everything that you see in the parentheses. You would have to simplify that, and you would still have your b value. Okay, looking at the first set of examples. This one says Christy invests $300 in an account with a 2% interest rate. Assuming Christy does not make any other deposits or withdrawals, what will Christy's account balance be after 20 years? And we're looking at this two different ways. We're looking at it compounded annually, and we're looking at it compounded daily. So I'm going to start with the compounded annually. I'm also going to start by writing out the formula I gave you above. We have A, which is the amount earned, is equal to the principal multiplied by 1 plus the rate over the number times compounded raised to the power of number of times compounded times time. And next I'm going to label all of my key parts. So starting with our principal amount, that's the starting point. Our p-value, we'll do this off to the side. Our p-value is 300. She's starting with $300. Next, let's look at the rate. So the rate of this is the interest rate she's earning. In our description above, we have a 2% interest rate, which as a decimal is 0.02. And I'm locating that right there. The next piece of information we need to fill in is the number of times compounded. This specifically tells us that it is compounded annually. And if we scroll up to look at our chart, annually says that you have an n value of 1. This tells us our n value is 1 for this equation. Lastly, we need to look at time. How long is Christy investing? This says we want to know what Christy's account balance will be after 20 years. Of course, we could change the time. I could say to you, what would it be after 25 years? Or what would it be after 30 years? But in this particular example, our t value for time is 20 years. I'm going to fill all of this in, giving me an equation of 300 multiplied by 1 plus the rate of 0.02 divided by the number of times compounded, which is 1, raised to the power of 1 times 20. And when you type this into your calculator, I know this one's not going to make much of a difference, but in future problems, when you type this into your calculator, you have to make sure you have parentheses around this fraction as well. So you're going to end up having 2 sets of parentheses right here. You should all practice typing this in. Make sure you get the same thing as me. When I type 300 multiplied by 1, open parentheses, 0.02 divided by 1, close 2 sets of parentheses, raised to the power of 1 times 20, my answer is $445.78. Obviously, if you are working with money, you're going to round to the nearest hundredth, which is 2 decimal places. So this here is how much money she will have in her account after 20 years. Okay, she started with $300. So if I ever asked you the question of how much did she earned an additional $145.78. I know that's not the question there, but there are going to be questions like that. Okay, now next we're going to look at part B, which is compounded daily. For compounded daily, we're going to have very similar values, but now our n value is going to change. So let's do the same thing. Let's fill out all of our values. We still have a lot of the same info. Our principal amount is still 300. Our rate is still 0.02. We do need to change our time, or the number of times compounded, because now we're looking at compounded daily. Compounded daily is when you have an n value of 365. So that's the only piece we need to change in this formula. And when I substitute these values in, I have 300 multiplied by 1 plus the rate of 0.02 divided by the number of times compounded, which is now 365. This is raised to the power of 365 times the time of 20. Again, you're going to want to make sure you put parentheses around this fraction, or else you will end up with the wrong answer. When I type this into my calculator, I have 300, 1 plus parentheses 0.02 divided by 365, close 2 sets of parentheses, raised to the power of 365 times 20. My solution is $447.54. So if by chance the question says how much more did she earn, she earned an additional $147.54. If by chance there's a question that says which bank account, meaning this one or this one, would earn you more money, compare your answers. Which one gives you more money? So in this case, compounded daily would give us more money. Again, that's not the question, but those could be different types of questions. All right, so there's one other formula that we're going to go over today, and then we'll save the last one for tomorrow. But this one is continuously compounded interest. So continuously compounded interest has a slightly different formula. It does use some of the same letters, but we have something a little bit different that we're going to use, and it's called the number E. So we'll talk about that in a second. But we have our account balance, which is going to be our solution. And in the formula, we still have our principal amount, so the starting amount. This right here, hold on. This right here is a button in your calculator. All right, so that's not a value that we're substituting anything in for. That is literally a button in your calculator. This is going to be raised to the power of your rate multiplied by the time in years. Again, if you are given the time in months, you need to convert that to a decimal in years. So I'll show you where the number E is in the calculator once we go over a couple of these problems. For the first set, it says, suppose you won a contest at the start of 9th grade that deposited $3,000 in an account that pays 5% annual interest, compounded continuously. You start college 4 years later, and you spend 4 years in college. About how much will be in the account after 4 years of college? So you have to be careful because these word problems are all going to be mixed up, so you need to pay attention to the language. The word problems are going to tell you what type of formula to use. Right here it says compounded continuously. That tells you that you are using the compounded continuously formula. So that tells me that I'm using the equation A is equal to the principal amount multiplied by E raised to the power of rate times time. My principal amount is the starting amount, which in this case is 3,000. E is going to be in our calculator. Next, we need to look at the rate. And the rate tells us it's 5% annual interest. That would be as a decimal 0.05. And lastly, we're looking at time. This says we want to know after 4 years of college how much will be in the account. Well, we earned it at the start of 9th grade, 4 years later, and then 4 years in college. That makes a total of 8. 9th grade till you graduate is 4 years, 4 more years in college, that's 8. When we substitute these values into our formula, we have 3,000 multiplied by E raised to the power of 0.05 times our value of time, which is 8. And now I'm going to switch and show you in Desmos Scientific Calculator how to type in the number E. Okay, in Desmos Scientific, we have 3,000 multiplied by E, so I'm going to select function, which is directly below my cursor, slid over to the right. Hit function, and now if I'm looking at the right-hand side keys, I'm going to go 3 rows over. I see that I have what looks like an E raised to the power of X. I select that, which drops in my number E, and now gives me the opportunity to type an exponent, of which I type 0.05 multiplied by 8. And you can see I get $4,475.47. So starting off with $3,000 at an account that earns 5% interest, 8 years later, this account earns an additional $1,475.47. Okay, I'm going to do the on your own section by myself. You guys can watch as I do that. And we're going to stop right here today, saving the last part, which is population, for tomorrow's video.